have here is the solution to the Northstar case. And the data that is given to you once you read the case is that a lady's looking for some shirts to sell at events, and we have the probabilities for the events and this, that, and the other thing. What we do know as our our variables, yeah. And we've got 4,000, 6,000, and 8,000 different purchase quantities that we can have. So we're going to go to this event, we're going to sell shirts, and it's going to cost, and we're going to make some money on it.
Yeah.
You've got your profit per shirt, which
was that number provided, or
these numbers were provided?
Okay. Yeah.
And it actually comes in the form of you've got $12 a shirt. You're going to sell these for $12 a shirt. And for each shirt, it costs you whatever the inverse of this, minus 12. So it costs you $4.44 a shirt when you buy 4,000.
Oh yeah.
It costs you $7 and oh wait, what?
You locked it.
Oh, that would be silly.
Throwing dollar signs. Okay, so you basically just reverse engineered the.
Yeah.
So yeah, this is just.
So this is your price per shirt for each purchase order quantity. So we have our profit per shirt, but let's backtrack a little further. The first thing that you need to look at is how many people are going to be at the concert or the event, and what the likelihood is that they're going to buy a shirt.
Okay.
So shirt sales distribution, this is based on historical information as it says in the case.
Yeah.
And it is a distribution of, it's a triangle distribution that you make in at risk, or risk 6. And the values, your low value is 0.05. Your medium value is 0.10. Your high value is 0.18. So 5% chance, 10% chance, 18% chance. And at risk, what you do.
And here, just backing up slowly here. Those chances are the percent of people you think you can sell to of the total attendees.
Correct.
Okay, so this is saying 5%, 10%, or 18%.
Yes.
Okay, so percent of sales. Per total attendance.
Yes.
Okay, and that's the low, medium, high. Okay. Perfect.
Yeah, that's the low, medium, high. You also have attendee distribution. Let me zoom in here a little bit. You have your attendee distribution, which that is also provided, and it's also a triangle distribution. And the low value for it is 25,000. The most likely value is 50,000, and the high value is 90,000. So the distribution that you get is centered around 50,000 people coming to it, but it tapers off to 25 and to 90,000. So you have a less likely probability of those happening. Okay?
Okay. Yes.
So what you do is you want to find the number of shirts that you're likely to sell. On any given night at this venue for this event, how many shirts are you going to sell? Simple as that. And so when you take this distribution, this 15,452, and you multiply it, and you multiply it times 56,110, which is the people expected to go, you get 8,670, which means you're going to sell roughly 8,600 shirts at the event.
Now, for looking at the both of those distributions, which are triangle distributions, are those numbers necessarily going to be static? Are they going to be the same for every single person who's doing this assignment, or are they going to be like basically the thing I don't necessarily understand about a triangular distribution
Mm-hmm.
is it always going to be some number averaged between those three, or is it just you've rolled the dice 10,000 times and the most likely distribution is at 15%? Do you understand what I'm saying?
So this is actually what it looks like.
Okay.
This is your distribution, meaning you have 90% chance that there are going to be X number of attendees at the event.
Mm-hmm.
Okay. And so down here's our low value, 25,000. Up here's our high value, 90. And within that, you're expecting 90% of all of your opportunities of attendance are going to be within here.
Cool.
Okay. You do the same thing with your shirt sales distribution. So that's what this looks like. Your low end you have over here is, hold on, 5%. You can see right there. Your high value is 18%.
Yeah.
And 10 is centered right around the peak. Okay?
Okay.
So that's what the triangle distributions look like. Now, once you multiply those two together, so we're looking at this value right here. Once you multiply those two together, you get an alternate distribution.
But on the last one, didn't you have, in the one in this one, you have 15% listed as the shirt sales distribution?
Yeah, so that's part of that is the, oh, there we go, that'll help. Is when you do this dice rolling thing,
yeah,
it consistently cycles through different values.
Okay, so this is, the most likely value is still roughly around 10, you
Yeah.
just happen to have it.
Yes.
Okay, yeah, okay, cool.
And so risk static right here, this is actually a way of just labeling what the default value is.
Okay, yeah.
So just keep that in mind. You've got your risk output, which that's what you need to put in order to get this distribution that I have showing. In order to get this distribution, you have to multiply those two values together. That value and that value. Let's just do that.
And then, okay.
Yeah, so there's your demand distribution.
So I guess my question one is why do you do the calculation as equals risk output as opposed to just doing equals D2 multiplied by D3?
So risk output is what basically takes.
It's the same thing, but like, is there a reasoning on using risk output in this situation as opposed to just multiplying?
Just doing two.
Yeah, just doing the two multiplied together.
Yes, and that's a function of the actual at-risk program.
Okay.
In order to get a distribution that looks like this, you have to have it, or you
yeah.
have to have it tagged as a risk output.
You have to have an output cell.
Yes.
Okay, cool.
Makes sense. And so that's what comes with it. Now, this, when you multiply those two together, this is the risk distribution that you get. You're saying, and kind of as your low end, if you 1,500 shirts is kind of the lowest that you're going to sell, and you can actually sell 8,000 is what you're capped at, but
because that's the most I could have bought
most.
in the highest possible
Yes.
scenario. Okay,
yeah, but if you look at the long tail here, like right around 15,000, there's still a number of sales that occur with 15. So you could almost double up on that, but you can't because you're capped at 8,000.
So yeah, even though if I had those, I would have a pretty low chance of selling that many, but
Yes.
still possible.
Yes.
Cool.
Okay. So now that we understand the number of shirts that are going to be sold, now we have to start looking at the cost of those shirts. And like, how's it going to look when we sell different quantities and we sell it,
Different attendance rates.
and things like that. That's the flow that we're going for.
Okay.
So what you do, the first thing that you do is you look at your supply. And that is, you have 4,000, 6,000, and 8,000 shirts that you can purchase.
Okay.
If you go with the so I'll explain simulations here in a bit,
Mm-hmm.
but just keep this as a note. Risk sim table basically allows you to run the same statistical scenario with 3 different data sets. And so what this equation shows is risk sim table is basically just like a checklist of different values to use in the simulation.
Yeah.
And so you have one for 4K, and it's here. Let's just do this. Okay, so you have 4,000, 6,000, 8,000. Simulation 1, you're going to run these values. Simulation 2, these values. Simulation 3. And if you look at so E, F, G is basically the progression. So it does E first, then row G, or row E first, F, and then row G, right?
And this is taking in data from the shirt sales distribution and the attendee distribution for each simulation.
Yes.
Okay, so each simulation is that. The other question I have is the loss if canceled.
Yes, we'll get there.
Okay.
We'll get there, don't worry. I'm just working straight down
Yeah,
this.
no, this is good.
You do the same thing for profit per shirt, which means that it'll run the same profit for all 4,000, it'll run the same profit for 6,000, and the same for 8, and it'll run this value correlated with this, not correlated, but this value grouped with the 8,000.
Okay, yeah, so it's going down each column.
Yes.
Cool.
And same for loss if canceled, which we'll talk about in a bit. But once you have your demand distribution, which is number of shirts sold, and you have your expected profit, then you want to make a decision on, then you have to cap there are a couple of different elements to this, right? The first one is if you sell more than 4,000 shirts, you can't, or if there are more than, if your demand is greater, your demand for t-shirts is greater than the purchase quantity, then you can only sell 4,000 shirts. So that is what this logic is right here. And it's saying if demand is greater than supply, then you can only use supply times your demand.
Yep.
Or no, not times your demand, it's your supply times your profit per shirt, because you've capped out.
Yeah. Okay, yeah, so it's saying don't take the total demand in the one situation that in the probability that you sell out all the shirts, don't sell out more than 4,000. You can't sell 4,001 shirts. In all the situations that you sell 4,000 shirts, in scenario A, you can only sell 4,000, so it caps it.
Absolutely. So that's the first part, and then what happens is, and this is kind of a twist that came in the story. It's if the event happens, you can sell back any unsold shirts for $2.75 a piece.
Okay.
So you sell them to thrift shops or whatever, but you can get $2.75 for them.